Hello, I'm Pasavas, and today I'll be sharing my engineering project, optimizing internal structures of 3D printed objects for shock absorption. 3D printing has become an increasingly prevalent tool with multiple use cases all throughout the industry. And by being able to design an internal structure which would optimize shock absorption, it would act as a baseline and as a guide for designers and industries looking to use 3D printing as a shock absorber. In this investigation, it was looking to create an internal structure which would absorb the most shock, all while minimizing mass and thus cost and weight. This project was looking specifically at thin prototypes about 3 inches thick in a low-speed collision at around 6.8 miles per hour at impact. In addition, this being infill, it would have to be a repeatable pattern, and the shock absorber would have to protect whatever was behind it. During testing, it would be extremely important that the impact speed would be the same so that the prototype would be hit with a constant impact speed as well as impact force. To achieve this, a pendulum-like device was created where the arm would swing down with the same force and speed every time. In regards to the prototype, each design iteration was tested 5 times to check for precision in the measurements, and each prototype was printed with the same print conditions and filament, which was PLA black. A large variety of data were collected. In quantitative data, this was force during impact, deceleration during impact, as well as the mass of the prototype. For qualitative data, it was the visual damage to the prototype, as well as a description of where the damage occurred, both of which would be achieved via photo and video during impact. For other data, it was whether the contact of a testing arm and the force plate. During data analysis, only the first impact, or the most significant one, was analyzed. The average of all 5 tests were calculated to determine the cost of the prototype, time of the impact, which was defined as when the accelerometer began reading a negative reading, thus a deceleration, until it began reading a positive reading again, the max force, as well as the max deceleration. The design was then analyzed with 2 indexes. Firstly, the mass force index, which was the max force times the prototype mass, and the max deceleration index, which was the max deceleration times the prototype mass times -1. In both of these cases, the goal was to get the lowest index possible, which would ensure that the prototype had the least amount of mass and thus was the cheapest, and had the lowest force and deceleration during impact. It was also a requirement that the force would be below 250 newtons and the deceleration below -245 meters per second, or 25 Gs. Lastly, it'd be considered a failure if the arm and force plate contacted, which would mean that the prototype did not protect whatever was behind it. The testing procedure was quite simple. It consisted of weighing and photographing the prototype, calibrating all the sensors, placing the prototype in its impact position, then beginning measurement recording, and then releasing the arm and letting impact occur. After impact, checking the prototype for visual damage and photographing it, and finally testing the same design multiple times. All prototypes were designed with SolidWorks and then sliced with FlashForward FlashPrint 5 with the same print conditions. The prototype was then printed on a FlashForward Adventure 3 Lite and printed with black PLA filament. The first prototype constructed was a standard hexagon, aimed to be a simple design purely to see how the prototype would break. Furthermore, a 2021 research paper had stated that the hexagon infill absorbed the most amount of energy during a low-speed collision, and it would be important to see whether this correlated with shock absorption. The photograph here shows the prototype H4 after impact, and it's worth noting that many of the failures were at these key corner pieces where all the sides of the hexagons converged. And it's also worth noting that the cuts that occurred, or the pieces that detached, were very straight edges going right down the sides, and that most of the damage occurred in this front section of the prototype where the arm had hit. The force chart also shows the damages, as these spikes that can be seen throughout it represent when the prototype failed and thus absorbed energy, reducing the testing arm's velocity and thus force at impact. The same can be seen with the acceleration chart, where these large spikes represent when the prototype failed, thus reducing the deceleration and resulting in these spikes. The time of impact can also be defined visually here, as it is the time it takes for the accelerometer to read a negative reading until it reads a positive reading, as can be seen in the chart. The chart here shows all the measurements as well as the evaluations of each prototype as well as the overall average. In this case, the prototype met all the requirements, including the force requirement, the deceleration requirement, and the arm and force plate did not contact, meaning that if something had been behind it, it would have most likely been protected by the shock absorber. The prototype costed about 51 cents, and the mass force as well as mass deceleration index were both around 5,000. The next design that was investigated was a zigzag design. The standard hexagon had failed at certain points, which had made it act as a spring, absorbing energy and slowing down both the testing arm as well as the force and deceleration. By creating a design that would exclusively act as a spring, such as zigzag, it would hopefully compress absorbing energy and thus reducing both the excess deceleration and the force. It's worth noting that only the shape of the internal structure was changed, nothing else. The thickness and the print conditions remained the same. As can be seen here, the prototype endured no visual damage that could be seen to the naked eye, and while the prototype did do much better in the acceleration, it did slightly worse for force. Now, both of the curves were much smoother, and this is because the prototype compressed in a much smoother way versus the hexagon, which had failed, resulting in much more abrupt changes in force and deceleration, thus creating many more spikes. Even though the testing arm and force plate did not contact, and the prototype met the deceleration requirement, it did not meet the force requirement, meaning that this prototype would be considered a failure. Furthermore, even if it had met both requirements, it still had a much higher mass force index as well as a mass deceleration index and costed about 88 cents. It seemed that the zigzag had reduced acceleration but not force because it had fully compressed, meaning it could not absorb any more energy when the arm hit the force plate. For the next design, a reversion back to a hexagon but thinner would allow the arm to penetrate through more hexagons, hopefully allowing for more failure since it seemed that the hexagon failing had helped reduce the force. More failures would hopefully then slow down the impact time and therefore the force and deceleration. As can be seen by the picture, the thin hexagon failed completely as the arm penetrated right through it. However, the failures still resembled the regular hexagon and were at these key corner pieces. The force chart does show a promising beginning, though, as the prototype fails. However, the testing arm eventually penetrates through the whole prototype and hits the force plate with a massive amount of force. As far as the acceleration, you can see a mass acceleration of about negative 300 meters per second. It's worth noting, though, that the accelerometer has a range of up to negative 245 meters per second, which is why this oscillation can be seen after the impact, as the deceleration is greater than the accelerometer's range. Even though the prototype did have a promising mass force index and deceleration index of about 5,500 and 3,600 respectively, it did not meet any of the force, deceleration, or arm and force plate contact requirements, making this prototype a failure, though the prototype costed only about 26 cents. The final prototype used everything that was learned in the previous testing, as the standard hexagon had resulted in the lowest impact force, while the zigzag had resulted in the lowest deceleration. By creating a common design, the hope was that the assets of both the standard hexagon and the zigzag could be combined to create a much better prototype. As can be seen in the image, the zigzag section of the prototype endured no visible damage. However, the hexagon section did endure damage at the same corner pieces as the other hexagon designs. The hexagon failures varied from the front section to the rear section, and no pattern could be determined. Both the charts show once again the spikes which result in when the prototype failed and thus absorbed shock. The smooth front represents when the zigzag compressed, and the more spiked rear is when the hexagon began failing, reducing force and acceleration in a more erratic fashion than its zigzag counterpart. This prototype costed about 66 cents, and there was no arm and force plate contact, meaning that it would most likely have protected whatever was behind it. The prototype also met all other force and deceleration requirements, even though its mass force and mass deceleration index was still a bit higher than the standard hexagon. These charts, the red bars represent the prototypes that did not meet any other requirements, while the green ones are the ones that did meet all requirements. It can clearly be seen that in both the mass force index and mass deceleration index, that the H prototype is still the clear winner. Like stated earlier, the best design was the standard hexagon and resulted in the lowest mass force index as well as mass deceleration index, only costing 51 cents. However, it's worth noting that it's very hard to create a standard design because every situation is unique and has unique requirements and different factors. For instance, a much thicker prototype could have made the standard hexagon be the perfect design. If I could continue investigating, I'd like to spend more time investigating combined prototypes. There are a few possible errors I'd like to briefly discuss. First of all, temperature and humidity could have both impacted the testing sensors, as well as the prototype properties such as flexibility and brittleness. Also, print discrepancies could have occurred, changing some of the prototype's properties. I'd like to take a moment to acknowledge the Great Mills High School STEM Academy, my family, and especially my father, Dimitri Savis, for their continuous support and help during this project. Thank you very much. In addition, raw data and any other files or more detailed procedures related to this investigation can be found in this Google Drive file below.